Welcome to another episode of Mr. Avila Physics. Today we're going to be talking about the graphs of motion. Now, sometimes it's very difficult to describe the motion of an object using words. So we use graph instead so that we can paint a picture of the motion of an object. Now, before we move into the graphs of motions, let's remember that motion is the change in position described by distance and time. Velocity tells us how fast the displacement of an object is changing and in which direction. And acceleration tells us how fast is the velocity of an object changing. The first type of graphs that we're going to look at is the displacement versus times graph. Sometimes these graphs are also referred to as distance versus time, but we have to be very careful of what goes on each axis. Because remember, there is a difference between displacement and distance. Displacement can be positive and negative, while distance is always positive. All right, so when making the graphs of these quantities, we have to be very careful of what we put on each axis. Now, for the most part, we will put time on the x-axis and displacement in the y-axis. This means that, right? The farther to the right that we go, okay, the more time has passed, and the farther away we are here on the y-axis, the farther we are from our starting point. And our starting point would be located here. Time moves on to the right, and we move away from our starting point in this direction. Or if we are moving in the opposite direction, we could also be moving away from our starting point in the negative y-axis. Because remember, displacement is a vector quantity, so you can go either positively or negatively. All right. Now, if an object is not moving, then its displacement does not change as time goes by. So if we were to graph this, we would have a horizontal line at displacement. Here, as time goes by, the displacement is always the same, right? It's constant displacement. Sorry, zero displacement because it never changes. So when this happens, we say that the object is at rest. Now, if an object is moving at constant velocity, it means that its distance increases by the same amount for each time interval. So we would have a graph like this. So if I were to choose a time interval from here to here, then I could find the change in displacement by just looking at here to here. And this would be my change in displacement, delta x. If I look at the same time interval but farther down the line, then I would see that the change in displacement here is the same, right? So I can say that delta x1 is equal to delta x2, which means that if the displacement changes by the same amount during the same time interval, this means that it is moving at constant speed, okay? Now, another way in which we can look at this is by trying to find the slope of this line. So if I were to find the slope of this line, I would do slope is equal to delta y over delta x. Change in y will be change in displacement, and delta x will be change in time. Now we've seen this definition before, change in displacement over change in time. This gives me velocity. So by finding the slope on a displacement versus times graph, I can find the velocity of an object. If this was a distance versus times graph, then I would be finding the speed of an object. Okay, so by solving this, I can say that the velocity of an object is given by the slope of the graph of a displacement versus time. All right. Now, what happens if instead of a straight line, we have a curved line? Then here, if I'm looking at one time interval here, I see a change in displacement of this much, delta x1. If I look at the same time interval here, then I see a change in displacement that is much greater. So I can say that delta x2 is much greater than delta x1. So if during the same time interval the distance increases and increases and increases, then we can say that this object is accelerating. It's not going at constant velocity, but it's accelerating. Okay. Now, another way that we can prove this is by looking at the slope of the tangent line at certain points. So if I look at the slope of the tangent line here, I would see this graph. If I go over here, I would see this line. And if I go here, I would see this line, right? So this is slope at one point, slope at the second point, and the slope at the third point. Now, I can see that the slope is increasing. And in the previous slide, we mentioned that the slope of a displacement versus times graph gives velocity. So here, the slope at the different points is increasing, which means that the velocity is increasing. And if the velocity is increasing, then that means that the object is accelerating. Now, what if we had a graph of displacement versus time that looked like this? Okay, then I could also see that the time interval on each if I do the same time interval here, I would have this change in displacement. And if I do the same time interval over here, then I can see that the displacement is a lot less. So I can say that delta x2 is less than delta x1. So the distance traveled during each time interval is becoming less and less and less, which means that the object is accelerating in a negative way. It is covering less distance as time goes by. Now, another way that we can prove that is by taking the slope of the tangent lines at different points. Let's say this point right here. If I'm looking at this point right here, then I see the slope of the tangent line is here, m1. The slope of this tangent line is here, and the slope of this tangent line is here. What do we notice? We notice that the slope of the tangent line is getting smaller and smaller and smaller. And since we said that the slope is equal to the velocity, then the velocity is decreasing, which means that this object is slowing down or decelerating or accelerating negatively. So we can find a lot of information from a displacement versus time graph. Now, let's look at all this information in a single graph, okay? So what have we learned so far? We learned that it's very important to label the axes correctly, okay? We've learned that a horizontal line on a displacement versus times graph means that the object is not moving, it is at rest. We've learned that an upward sloping line means that the object is moving away from its original position at constant velocity, okay? while a downward sloping line means that the object is returning to its starting position at constant velocity. We learned that the steeper the graph, the higher the slope, the greater the velocity. And that a curved line means that the object is accelerating, either speeding up or slowing down, depending whether you have a curve like this for speeding up or a curve like this for slowing down. So let's look at this in a single graph. Here we can see that the object's displacement is not changing, so it is stationary through this point right here. Here we see that we have a positive slope, right? So that means that it has a positive, it's moving away from its original position at constant velocity. Then here it is returning back to its original position at constant velocity, only in the opposite direction. Okay. Here we have a high slope, so that means that it's moving fast, but at a constant velocity. And here we have a curved line, which means that the object is getting faster. All right, let's look at some examples here. In which of the following graphs are both runners moving at the same speed? In which graph do the runners end at the same place? And in which graph or graphs is one runner going twice as fast as the second runner? Pause the video here, take a couple of minutes, and see if you can solve this example. All right, welcome back. Let's look at this. In which of the following graphs are both runners moving at the same speed? Speed is the magnitude of velocity. So, and velocity is the slope of a distance versus times graph. Okay, or even simpler, these are distance versus times graph. So the slope of this graph gives me speed right away. Okay, so I'm looking for a graph in which both runners have the same slope. And the only one that I can find is graph D, right? Where both lines have a slope of 10 changing y over 4, and this graph has a slope of, sorry, it did not 10, 5. Well, let's see. All right, so we can see here that these lines are parallel, which means that they have the same slope. So that means that graph D would be the answer to the first one. The second question, in which graph do the runners end at the same place? Okay. Then we are looking for a graph where the distance from the initial position is the same for both runners. So if we consider here the initial position, then in this graph we can see that both runners are at 30 yards away from the initial position after 4 seconds. In this graph we see that one of the runners is here while the other runner is here. In this graph, one runner is at 30, the other runner is at, looks like 15. And here we can also see that the runners are in different locations. So here the answer would be A. Now, for the last question, in which graph or graphs is one of the runner going twice as fast as the second runner? So twice as fast is a measure of speed. So we're looking for a graph where one slope is twice the other slope. So we can eliminate this one right away because the slopes are the same. Let's look at this one right here. The slope here is from 10 to 30. That's a change in y of 20 over 4 seconds. The slope here is 10 to 30, right? That's a slope of 20 to 30, that's a slope of 10 in 4 seconds. Here, this slope is a change of 10 in 4 seconds, and this slope right here is a change of 20 in 4 seconds. Here, this slope is a change of 10 in 4 seconds, and this slope right here is a change of 1, 2, 3, 30 in 4 seconds. So it looks like the only graphs that comply that one of the slopes is twice the other is graphs A and B. All right, let's look at this next example. The following graphs represent the motion of a car. Match the descriptions with the graphs. The car is stopped, the car is traveling at constant velocity, the velocity of the car is decreasing, and the car is coming back to its starting point. Pause the video here, take a couple of minutes, and see if you can solve this example. All right, welcome back. Let's look at this right here. So for the car to be stopped, the displacement needs to be the same as time goes by, and the displacement does not change. The only graph that satisfies that is graph C. Cars traveling at constant velocity. Constant velocity means that the slope of the displacement versus time graph is the same through all points. Two graphs satisfy that, which is A and B. I guess some of you could argue that C also has the same slope, right? A slope of 0. But an object not moving does not have velocity. It has a velocity of 0. So we cannot say that it is a constant velocity as time goes by. It is not moving. The velocity of the car is decreasing, right? We only have one graph that shows acceleration. And in this graph, we can see that the slope of the tangent line becomes less steep as time goes by. So the velocity is decreasing. And the car is coming back to its starting point. We see that in this graph, it's going away from its starting point. In this graph, it started somewhere over here, and it's moving towards the initial point, which is this one right here. And in this graph, it is not moving. And in this graph right here, it is moving away and away and away from its starting point. So this would be graph B. All right. The next type of graph that we're going to look at is a velocity versus times graph. Okay. Not to be confused with the speed versus times graph. Most of the characteristics are the same, except for a couple of things. A velocity versus times graph could be negative. It could go below the x-axis, while a speed versus times graph must be above the y-axis. The x-axis, sorry. All right, so the first thing that we have to look at is where do we place our quantities? What quantity goes on each axis? And since time pretty much always goes on the x-axis, that means that velocity would go on the y-axis. And if we have a straight line on a velocity versus times graph, it means that the velocity does not change. The velocity of this object is constant. It does not mean that the object is not moving. In fact, this object is moving at constant velocity. Okay, so all right, now let's look at our next graph here, which is a graph where the velocity of the object is changing by the same amount for each time interval. So if I look at this graph and I look at a time interval here, I notice that the change in velocity is here. If I look at the same time interval over here, then I notice that the change in velocity is here, and I can say that delta V1 is equal to delta V2, which means that this object is changing its velocity by the same amount as time goes by, which means that this object is accelerating. Okay? Another way that we can find this out is by looking at the slope of this graph, which is delta y over delta x, which is delta v over delta t, which is acceleration. So we can say that the slope of a velocity versus times graph is the acceleration of an object. Now, what happens if we try to find the area underneath an acceleration velocity versus times graph? So what happens if I try to find this area right here? Right? Now this area looks like a triangle, and I know that the area of a triangle is equal to 1/2 base times height. So in this case, it would be 1/2 time times velocity. What happens if I multiply velocity times time? Well, let's do a unit analysis. What are the units of time? Seconds. What are the units of velocity? Meters per second. So if I multiply this, the seconds cancel, and I end up with meters. And what quantity is measured in meters? Displacement. So if I try to find the area underneath a velocity versus times graph, this area would give me the displacement of the object from time equals 0 to time equals t, right? Whatever this value is of time right here. Okay, so a lot of information that we can find from a velocity versus times graph. If we look at this in a single graph, it means we can find out several things, right? A horizontal line means that the object is moving with constant velocity, okay? A positive slope means that we have positive acceleration, okay? Acceleration is positive. A negative slope means that acceleration is negative. That means the object is slowing down from going very fast to stopping, okay? When the velocity is 0, the object is stopped, not moving, okay? Remember, velocity 0 means you're not moving. All right, so what else can we find from here? We can find the total displacement of the object. If I break this down into several pieces, right? And I find this area plus this area plus this area plus this area plus this area. So then the total displacement would be equal to area 1 plus area 2 plus area 3 plus area 4 plus area 5. All right, let's look at some examples. The following graphs represent the motion of a car. Match the descriptions with the graph. All right, pause the video here, take a couple of minutes and see if you can solve this example. All right, welcome back. Okay. The first description that we have to look at is the car is stopped. When an object stops, this means that the velocity is equal to 0. Means you're not moving. There's only one graph that shows velocity equal to 0, and that is graph H. Car is traveling at constant speed. Okay. Constant speed means that the velocity is not changing, the speed is not changing. Only one graph shows constant speed as time goes by, and that is graph G. Car slowing down, that means that the velocity is decreasing. So you're going back towards 0 velocity from a certain value towards 0 as time goes by. So that would be graph F, and speeding up would be graph E. You're starting at velocity 0, and as time goes by, you are increasing your velocity until you reach a certain value. All right, let's look at this next example. Choose the correct words from the following list to describe the motion during each segment of the journey. Accelerating, decelerating, constant speed, at rest. Pause the video here, take a couple of minutes, and see if you can come up with the answer to this question. All right, welcome back. So let's look at this first. The first thing that we have to look at is the axis on the graph. Here we see a velocity versus times graph. So here from O to A, we see a positive slope. Positive slope means acceleration, so it is accelerating right there. From A to B, I see a horizontal line. Horizontal line means the velocity is not changing, right? So we have constant speed. From B to C, I see a negative slope. I see my velocity going from 10 to 0. So this is accelerating negatively, which is the same thing as decelerating. From C to D, I see that the velocity is at 0. So velocity is equal to 0. That means that the object is at rest. D to E, positive slope, accelerating, and E to F, horizontal line, constant speed or velocity. All right. Thank you all for watching. See you next time.